So I'm back with an illustrative example for simulation. It's like a very basic example only for the illustrative purposes. So suppose you have a population. Again, this example is specified in the slides that are posted. So suppose there is a population of size 3. If you've taken some courses with me by now, you know this example by heart anyways, which I use all the time to explain standard error, the sampling distribution of the mean. So population of size 3 with mean equal to 2. So there is nothing really to study here. This example is just for illustrative purpose because this population is so small, there is no need for statistics or statisticians in this population. But let's say for some reason we wanted to study this population using a sample of size 2 only. So in this situation, rather than simulating samples of size 2, we can actually enlist all possible samples of size 2, which helps us in kind of verifying several results that we talked about earlier. So the samples that are possible are 1 and 2. Let me make some more space before my ugly handwriting takes over everything. So samples, I get 1, 2, I can get 1 and 3, and I can get 2 and 3. Now, because I'm interested in mu, so this is my theta or the target parameter. So T here is theta hat, which is y bar. So the mean of 1 and 2 is 1.5. That's my T1. 1 and 3 will give me 2. That's my T2. This will give me 2.5. That's my T3. And we can also calculate S over S and S. Let's first calculate S. And S over square root of n. We can calculate test statistic, p-value in the bracket, and we can construct confidence interval. So I did some stuff beforehand. 1.4.1, 0.0, 0.5. Test statistic theta equal to theta naught versus theta naught equal to theta naught is this. You can use R to get these values. If this was your sample, this is the value of test statistic, and the corresponding p-value is this. Similarly, you can get the confidence interval. Need more space. To 7.8 minus 10.7 to 14.7 and minus 3.8 to 8.8. So this is the table of sample statistic. So one Monte Carlo estimate of mean. Is theta hat, which is TS. S goes from 1 to S over S, which is T bar, which is basically the mean of this column that you see. So 1.5 plus 2.0 plus 2.5 divided by 3, which is 2. Monte Carlo estimate of bias is T bar minus mu, which is 2 minus 2, which is 0. So this is an unbiased estimate. Next step, Monte Carlo estimate of standard deviation. Ts minus T bar whole square S minus 1, which is basically the variance of this column. So let's call it column C1. So in R, this is mean of C1. In R, this is variance of C1, square root of that, right? So it's 1.5 minus 2 square plus 2 minus 2 square plus 2.5 minus 2 squared over 3 minus 1, which is 0.5. You can also calculate Monte Carlo estimate of mean square error, just denoted by MSE hat, which is 1 over S. S goes from 1 to S. Ts minus mu whole squared, which would be again the same thing because it's 1. Mu and T bar are same, right? So it's just going to be, the only difference is that the denominator is S and here the denominator is S minus 1. So it's going to be 1.5 minus 2 whole square plus 2 minus 2 whole square. This 2 is mu, this 2 is T bar, plus 2.5 minus 2 whole square divided by 3, which gives you 0.4. Now we can check the performance of these estimates of uncertainty. So standard error of y bar is S over square root of n, where S square is 1 over n minus 1, sum yj minus y bar whole square, j equal to 1 to n. So we already calculated that. So the it's average of estimated standard error would be 0.5 plus 1 plus 0.5 divided by 3, which is 0.67. If I go back, it's basically the average of this column. Let's call it C3. So it's the average of C3, which is 0.67. And Monte Carlo standard deviation estimated was 0.5. So it's not that bad. Now you can also do simulations for properties of hypothesis tests. So if H naught is mu equal to mu naught versus H1 is mu naught equal to mu naught. You, let's say, used a t-test for that and you get these values in column 4. P-values are, all these p-values are big. So if they were small, you would have rejected. So you fail to reject, you fail to reject, you fail to reject. So in our case, you fail to reject all 3 times. So your alpha is 0.05. In our case, we fail to reject 100% times, right? Alpha 0.05 means probability that you reject H naught given H naught is true, right? So the probability that we reject H naught given H naught is true in our case is 0. Whereas alpha is 0.05, so it's pretty far away. So this is the achieved alpha, or Monte Carlo estimate of alpha. You can again also, this is for confidence intervals. Let me write full form. And the last one is you can also calculate coverage probability. It's the, so suppose you calculate the 95% confidence interval y bar plus minus t times standard error of y bar. That's what we did here in this column, C5. Now what you can do is, does the interval achieve the nominal level of coverage that is 1 minus alpha or not? So for our example, all these three intervals covered the true value. The true value or the nominal coverage is, so basically all of them have they cover the true value of the mean, whether it is this one or this one. So that means the proportion or coverage probability is proportion which cover true value is, sorry, I should say percentage, maybe, is 100%, right? All of them covered, but you count the confidence coefficient or observed nominal or the nominal level that was advertised was 95%, but the coverage probability or observed nominal level is 100%. So over coverage, that's also an issue. It should not, the interval estimates should not have under coverage or over coverage. So in this example, there is over coverage. So that's pretty much it. All of it is in the slides again. So check them out. Don't forget to check them out. And I'll see you guys in another video.